Okay, from the next class, we want to be giving out token numbers to students. Skipping it this class, looking next class, right? So this we got to figure out a way of getting a token number to all this. You know, it's the third week of classes when the classroom is empty. By the time we get to the 14th week of classes, I'm teaching myself. And that's why I have to resort to all kinds of strange things to bring people into class. All right, can we begin? Okay, kids, shut your laptops, please. All of you. Okay, let's start. Over the next few classes, we will look at how to optimize the training of your neural network. Now, here's where we were so far. We've seen that neural networks are universal approximators. They can model pretty much anything, but we must train them to approximate a given function. And they're trained to minimize the total loss on a training set. We do this through empirical risk minimization and use variance of gradient descent to do so. So the gradient of the error with respect to the network parameters is computed through backprop. Raghav, how many people do we have in Zoom? 80. And we have a small number in class. So we're going to have to post attendance numbers today, starting today, okay? So the way we did this was like so. We defined a total training error, which was the average divergence over the entire training set. And we computed, we used gradient descent. So at each iteration, we went through the entire training data. We computed the average divergence, the loss, and how much that would change with the perturbation of each parameter, and modified the parameter accordingly, right? Always to decrease the loss. So we had, and of this, so when you train the network for each instance, we had to first pass the instance through the network in order to compute the locations and the intermediate variables. Then we pass the gradients of the divergence back through the network, and that passing of the gradient to the back through the network was what we call backprop. And once backprop was completed, we use the gradients that we had computed to update the model parameters. Right? So here's your first quote. Okay, are the polls not released or what? The polls must be released. 295? Or is the number off? Oh my, yes, you know what has happened? The numbers are 299 through 295? Yeah, 295 through 299, okay. All right, time's up. Sorry. I'll give you a few seconds. Okay, Somebody on Zoom, you want to answer this question? Backpropagating from the kth layer, which is what is the derivative for the weights wk? Anyone on Zoom? Which option's right? Hello, is there anybody on Zoom?
Yes.
Okay, so which is the correct option?
Or the first option.
First option. Do you guys agree that the first option is the right one? Yeah, so the way we defined it, we said at any layer, you had the previous yk minus 1, which influenced zk, which influenced the divergence. And so we saw that the derivative of the divergence with respect to wk was this yk minus 1 times the derivative of the divergence with respect to zk. And we saw that this is a row vector, this is a column vector, the product of the two will be a matrix of the right shape, right? Any other operation is not going to give you a matrix. So this works. Anyway, moving on, right? Any questions so far? Any questions? Questions on Zoom? Okay. So does backprop always work? We're going to start with that. Again, guys, shut your laptops if you're not. I know you're taking notes, I understand, but still, right? I'd rather you're looking up here than at the slides. Okay. So here's what we said. Let's look at whether backprop is always right. And I'm speaking of not when backpropagation finds a local and erroneous minimum. When backpropagation actually finds the global minimum of your loss function, is it doing the correct thing? So here is what we saw, right? We saw this example where we explained why we wanted a differentiable activation function. So what was the reason we wanted a differentiable activation function, Prachiti? Why did we want a differentiable activation function?
So that we could know if the distance between the activation function and the points was decreased.
We wanted to know how the error changed as we modified things, right? But then, and so in the upper picture, if all you're doing is counting errors, if you slide that figure left or right, the count of the errors will not change till you actually go over a training instance, right? So on the other hand, the one in the lower picture where you're actually looking at the total distance, any shift of the function changes the total distance, which is why you wanted two things. What were the two things you needed?
The two things needed was to just to compute the distance.
No, so for this to work, we had two requirements. What were those?
That your activation function is continuous and differentiable.
Perfect. And what was the other one? Krishna? We had a second requirement. What was that? The divergence must also be differentiable, correct? So this is fine. And now, once we have that, we can figure out which way to go. But then, when we actually use the network for inference, you're going to be performing classification, right? And when you're performing classification, you're going to be saying, you take a look at your function, and you say if the function value is greater than 0.5, the output is 1. If the function value is less than 0.5, the output is 0. And using the second picture at the bottom, where you're actually looking at the distance, if you optimize that to minimize the distance, total distance, will that also minimize the classification error in every case? Possibly not. Why not?
I'm just thinking where, for example, if like the positive and the negative values tend to overshoot where the classification happens.
So they are overshooting. No, so that's not the kind of situation where you will have it, right? The situation you will have it is where I have my training data. And so remember that the function doesn't actually ever become 1 or 0, right? It just keeps getting closer and closer and closer and closer and closer. So let's say I have like 10 raised to 8 points out here. And I have a couple of points out here, right? Then my function is something like so. It doesn't quite go to 0. What happens? These two are only going to contribute a small amount of cumulative data, cumulative error. Those guys at the end, although each of them is only contributing an infinitesimal amount of error, cumulatively it's going to be a whole lot. And so they're going to keep pushing the curve back, because in this case, when the curve is out here, like so, although these two guys are giving you bad error, these cumulatively will give you so much lesser error that overall you're better off, according to the objective metric that we have chosen. That making sense? Right? And so, although you're minimizing the loss as we defined it, it's not actually minimizing the classification error. And this is a common enough thing that can happen. So what this means is that, wait a minute, what's going on? Here's a very nice example by Brady, Raghavan, and Saloni from 1989, going way back when. Does backpropagation always separate? And so we're going to be comparing two kind of activation functions, the threshold activation versus the sigmoidal activation, where we're using a loss function, right, as we defined it. And so let's say you have the red classes and the blue classes. Are these linearly separable? Yes. So if I were to use the perceptron learning rule, which we saw worked with threshold activations, would it separate the classes? It would, right? Yes or no? Yes. Right. It would find something like the red line, right? And so would backprop, because that's the one that's actually separating the two classes. But then, suppose I add just one spoiler here, a red dot just to the bottom right. Now the classes are still linearly separable, right? And would the perceptron rule find a decision boundary in this case? Yes. It's probably going to find something like the dotted line, right? But then the number of blue and red points is very large. So what would happen to the backprop based decision boundary? Is that also going to swing out here? No. That's probably going to shift just a little bit, because one training instance doesn't contribute so much to the training error in the big scheme of things, right? Again, this changes if I have unbounded solutions, because when I have unbounded solutions, the sigmoid becomes a threshold. But anytime I want a bounded realistic solution, you're going to end up with something of this kind, right? Now, on the other hand, so what happened? The perceptron rule swung your classification boundary from here all the way out here, whereas the backprop based rule just changed it a little bit, right? And on the other hand, if I put my spoiler up there, what happens? Will the perceptron rule still separate the two? The classes are linearly separable, right? It's going to separate the two. What about backprop? It's still going to it's not going to change the boundary very much, right? I move the spoiler here. What happens? The perceptron rule gives me a different boundary. Backprop is not going to give me that boundary, right? Yeah.
You argue that
You can make various arguments, but let's get to a different question, right? So here, what happens is I can just move one training point, and if I move one training point, my perceptron classification rule is going to swing my decision boundary out widely to capture that one training point. Backprop is not. So what is going on over here? The perceptron rule is, in every case, the classes are linearly separable, and the perceptron rule is always right. But is the backprop based solution always right? No, right? So of these two, which would you choose? Why? it is less susceptible to outliers, right? So the backprop, the perceptron rule is what is called unbiased. It's always giving you the correct answer, but it has a huge variance. If I move 1 point, the solution can go from here all the way to here, right? Backprop is biased. It may not give you the correct answer, although the correct answer exists, but it's not going to swing around with a small amount of change of the data, right? So it has low variance at the cost of some bias, and the perceptron rule has high variance while remaining unbiased. And from our perspective, we want the former. We don't want the solution to swing around like mad just because you moved 1 or 2 training points, right? So although backprop is not actually finding the solution that you want, it is nonetheless giving you, I mean, it's not necessarily finding the solution that separates, it's nonetheless giving you the solution that you want, right? So the perceptron changes greatly upon adding just its new single training instance, but it fits the training data well. It has low bias but high variance because it swings wildly in response to small changes in the input, whereas the backprop based solution is minimally changed by adding just one more new training instance. It prefers consistency over perfection, right? It's a low variance estimator at the potential cost of bias, and this is something that we actually like. Now this was for a single linear separator, but when you go to nonlinear problems, the same thing holds. So here is a network which can maybe capture smooth functions of this kind, and then so it's captured a function that separates the blue dots from the red dot. If I add just one, wait, what happened here? If I just add one dot over here, up there, right? You don't want the solution to swing around and give you something completely different. Maybe it will move just a little bit. And this, from our perspective, is a feature, but from the perspective of specific problems, it might be a bug in that might not be an outlier at all, right? So something that we always are likely to encounter. So the fact that it's low variance at the cost of bias is something that is either beneficial, or in some odd cases it can be a problem. But in general, if you have enough data, then you expect that this is the kind of solution you want. You want a low variance solution, right? So backprop will often not find a separating solution, even though the solution is within the class of functions learnable by the network, right? Like in the case of the linear separator. And this is because the separating solution is not a feasible optimum for the loss function that we are looking at. That because the loss function for backprop is not classification error, it's a proxy to classification error, and where it has a minimum may not be where the classification error itself has a minimum. And so there's no guarantee that minimizing the loss will always minimize the classification error, right? One resulting benefit is that the backprop trained neural network has lower variance than an optimal classifier for the training data. So the optimal classifier could still separate the training data, the backprop trained classifier might not. Here's the second point. Okay. Someone on Zoom, can you answer this? Someone on Zoom. Guys on Zoom, I need your answers. Otherwise, I don't know. True or false? False, okay. Everybody agree that it's false?
Yes, false.
Thank you. Minimizing the differentiable loss function will also minimize the classification error. No, absolutely not true. The two are actually very different things, right? They're related, but they're not the same. So lesson 1 for the day. Lesson 2, let's look at the problem of optimization itself. all of these things, statements that I have made so far, assumed that somehow backpropagation and gradient descent are going to find you the global optimum. But the loss surface is often going to look something hideous like this. This is, the statement I made about the variance is assuming a global optimum. But the actual loss surface can be a really ugly thing. And will we even find the minimum? And does it even matter, right? So what does the loss surface look like? The popular hypothesis is that in large networks, the loss surface is not going to be a nice little bowl of any kind. You're going to get lots of saddle points. Saddle points are where the derivatives are locally flat, but then along some directions the function is curving down, and other directions the function is curving up, right? And so that the loss surface has many such saddle points. Another hypothesis, now all of these are hypotheses with some math behind it, and these are valid for some classes of losses, but not in the general case. We just assume that it is, that the loss function has many minimal local minima, but all of these local minima are more or less equivalent, in the sense that at these local minima, the loss function, the value of the loss, doesn't vary a whole lot, right? So in terms of training, if you're just using gradient descent, you're going to get saddle points of this kind very frequently, and your training is likely to get stuck on saddle points because it's going to go down the slope this way and just end up at the saddle point, right? So what we have, the story so far, we'll continue on that theme, but the story so far, neural networks can be trained via gradient descent that minimizes the loss function. Backprop can be used to compute the derivatives of the loss. It is not guaranteed to find a true solution, even if it exists and lies within the capacity of the network to model, because the optimum for the loss function may not be the true solution, right? And for large networks, the loss function may have large numbers of unpleasant saddle points or local minima, which gradient descent might just find. Okay. So now, so far so good. We've considered the fact that there may be multiple minima, and that gradient descent may actually end up in the wrong place. But then we've assumed that the training actually arrives at a local minimum. Does it even do so? And to do so, how long does it take? So we've had 2 lessons so far, right? Lesson number 3. We're going to see whether, even given an obvious minimum, gradient descent will actually get there. Now, an MLP is a really complicated function, and the loss function can be very complex. So we are going to look at it. There's something called the streetlight effect. You've all heard this joke. Some guy loses his keys in a dark bar, and he's found searching for it under a streetlight. And when the policeman asks him why, he says, well, I can't see anything in the bar. I can't see but this place is lit. So you're going to look at where you can actually make sense and hope that the lessons that you get from here can be carried over to the general case. So we're going to look at convex optimization briefly, right? So convex optimization is the problem of optimizing or minimizing convex functions over convex sets. How do you understand what a convex function? What is a convex function?
The screen share stopped.
Uh-oh. Paul? The screen share seems to have stopped.
Yes, it's doing that.
Huh? It's up? Okay. Thank you. So folks on Zoom, you should come to class. There's plenty of space here. Okay. So what do you understand by convex function? Anyone?
If you draw a line between 2 points on the
So convex.
if the line doesn't cut.
So that would hold true for both this and this, right? So a convex function is a function of this kind, where if I take any 2 points on the function and draw a straight line between the two, every point on the line is going to lie on or above the function, regardless of where I choose my 2 points, right? And now, how do you understand a convex set? What's a convex set? Firstly, is this a convex function? No, why not? I can just draw a line like so, and it's going to go below it. Now, a convex set is a set such that if I choose any 2 points within the set and I draw a line between the two, that all points on the line lie within the set. So this would be a convex set. You can pick your 2 points. I draw a line. The entire line is within the set, right? This is not a convex set, because if I choose this point, it's within the set. If I choose this point within the set, when I draw a line between the two, in this region, it's no longer within the set, right? So when we're speaking of convex optimization, we're speaking of convex functions where the solution space or the solution region is a convex set, okay? So we don't need all of these properties, but we'll just look at functions which have a bit of this property to see how, to get some idea of what can go right or what can go wrong, right? So now, when I'm speaking of gradient descent, these 3 figures are showing 3 different loss functions, and those continuous closed loops are showing equal value contours. So the darkest region is where the loss function is lowest, and if you walk along any line, all along the line, the loss function value is the same, right? And so the optimum is right in the darkest region. Now, in the uppermost figure, you're seeing a solution for gradient descent. You're taking steps, right? And what it's monotonically going towards the minimum. So that is a converging solution. In the second figure, it's sort of going towards the minimum, then it just begins to bounce around. That solution is jittering. It's never actually going to stop at the minimum. And in the third case, instead of getting closer and closer to the minimum, it gets farther and farther away. That's a diverging solution, right? We want a solution of the kind that's shown on top. We want converging solutions. So what are the conditions for convergence? For this, I'm going to start off by looking at quadratic functions. What is a quadratic function, anybody? What's a quadratic function?
Function where one, like the dependent variable square.
A quadratic function is a function of the second power of the variable, right? So if I'm looking at functions of a single variable, let's say f of x equals half times ax squared plus bx plus c. This half is only for convenience, so that when I take a derivative, the half and the 2 go away, right? And so this, what will the shape of a quadratic function be? Parabola, which direction?
Depends on the coefficient.
Okay, depends on which coefficient. A. Okay, if A is positive, what's it going to look like? If A is positive, it's going to be upwards, right? Everyone with me? If A is negative, downwards. So if I want a minimum, A must be positive, right? The second derivative must be positive for a minimum to exist. A is the second derivative, right? So now we know how to solve for the minimum of a quadratic. How do you solve for the minimum of a quadratic? Take the derivative and equate it to 0, right? So the solution for this is going to be 2 times half times 2a times x plus b, which is ax plus b equals 0, x equals minus b over a. Simple. In a single step, I can get the solution, right? But I can also solve for the derivative in a different way. I can start off at some initial point. I can take steps against the derivative till I get to the bottom, right? So if I'm taking steps against the bottom, then what is the approach I will use? I'm just going to start off at some x0, and I'm going to say xk equals xk minus 1 minus some step size times f prime of xk minus 1, right? That's what you would be doing. So at each point, the function has a slope, and you're going to be taking a step that is proportional to the slope in that direction, right? So now, if I'm using this derivative rule, this solution rule, so instead of solving for the global optimum, if I'm actually using gradient descent, is there a step size such that eta such that I will get to the solution in a single step? Meaning this way, is there a value for this parameter such that regardless of where I start from, I'll get to the global optimum in a single step? No? Yes? What do you think? So what this means is that regardless of where I am, if I start from here, if I use that value of eta, I'm going to get here in one step. If I start from here, regardless of the value of eta, I'm going to get here. I mean, regardless of for the initial point, if I use that value of eta, I'm going to get to the optimum in one step. What would this step value be? It's a quadratic, right? So what will this be? There is an optimal value, right? How many of you are familiar with Taylor series? Everybody's familiar. How many of you have heard the term Taylor series? Right? How many of you have never heard the term Taylor series? You guys have, right? Raise your hand. So have you heard the term Taylor series? Yes, okay. So now that because you didn't raise your hand, what is the Taylor series expansion of f of x at around x0? How do you derive the Taylor series? Anyone? Aman? Yeah, but I'm asking about the Taylor series, right? How do I take the Taylor series expansion of this function? You guys are very quiet. All of you have done Taylor series, right? So what's your name? I can't read it. You are Akriti. I'm trying to see hers. Shreya. How can you forget series? Okay, you move on. So anybody else? How do you define the Taylor series?
Do you equate the derivatives first and then?
So the Taylor series was this, right? At any point, I can say f of x equals, somebody want to give me this value? I want to take a Taylor series at some value x0, right? So this is my x0. How do I do my Taylor series? What is the first term? So, okay, here's the magic about the Taylor series, right? The Taylor series is what is it? There's a word in it, right? What is a Taylor? It's a Taylor what? It's a Taylor series. Can everybody say that aloud? Right? So it's going to be the sum of many terms, which goes on forever, right? The first term is going to be f of x0. Okay? So if you look at this, if I compute this right side is also a function of x, okay? The left side is a function of x. At x0, for the right side and the left side to be the same, what must the rest of the terms be? 0, correct? That's the only way that the series is going to hold at x0. So what can you tell me about what the rest of the term is going to be? It's going to be a function of x minus x0. Right, that way when I set x equals x0, the x minus x0 is going to cancel out. Right, and it's going to be a function that takes the value x, 0 when its argument is 0. So it's going to have some form. It will have several terms, but whatever the term it has, it's going to have terms of this kind. Somewhere in here must be an x minus x0. Right? So now I want the actual Taylor. I want not just f of the function, not just the function value x0, f, to be the same on the left and the right hand side. I want the first derivatives to also be the same on the left and the right hand side at x0. Then what would I do? Which means that if I differentiate both sides, they must be the same at, where's my Eraser. Was there an eraser? Okay. Okay. If I differentiate, so we agreed that the function must have this form, correct? Now I want a second term. I want f prime of x0. Now if I take a derivative of this with respect to x, what happens? What does it become? This is a constant, right? F of x0. So there's going to be a 0 over here, correct? And there's going to be some term here and some term here. What can you tell me? I want the next guy to be f prime of x0, right? And whatever remains to be functions of x minus x0 as well. Okay, so because these guys should not contribute to the first derivative. That makes sense? If I take a derivative of this term on the right hand side again, for this to be, I want both of these will become 0, but the next term must show up. So the Taylor series has this structure that is going to be f of x0 plus f prime of x minus f prime computed at x0 of x minus x0 plus half of f double prime of x0 x minus x0 whole squared plus and so on. And you'll observe that at x0 both sides have the same value. At x0 both sides have the same derivative. At x0 both sides have the same second derivative and so on. It doesn't matter if you truncate the Taylor series after n terms, then the left and the right side will have the same first n derivatives. That's the property of the Taylor series, right? So if I write this quadratic function out as a Taylor series, what is it going to look like? Over here, Tirth. I'm writing the quadratic function, this guy, as a Taylor series approximation around x0. What's it going to look like?
So it will be x plus 2ax plus b plus.
So what is fx0? I'll just call this as f of x0, right? Whatever it is. What is the next term over here, if I'm expanding it around x0?
2ax minus x naught.
You're going to get 2ax minus x naught, right? And then what would be the second term? Will there be a b? There's also going to be, this is going to be, it doesn't matter, right? I can just, the point is, if I truncate it after the second term, this is my Taylor series, correct? And will it be exact? It must be exact because the left hand side is a quadratic and the right hand side is a quadratic as well, right? There is no third derivative to a quadratic function. So the left and the right hand side must be identical, right? Make sense to everybody? So now let's look at this quadratic. When does this quadratic become a minimum? How do I solve for that? It's a quadratic. How do I solve for the minimum? Can somebody say that aloud? How do you solve for the minimum of a quadratic? Differentiate it and set it to 0. If I differentiate this with respect to x, what do I get? The first term becomes f prime of x0 because this goes away, right? And the second term becomes plus half times 2 times f double prime of x0 times x minus x0, correct? And these will cancel. Everybody with me? And in other words, I can say f prime of x0 plus f double prime of x0 times x minus x0 equals 0. Everybody with me? Right? In other words, x0, so I can say x minus x0 equals minus of f prime over f double prime, right? Computed at x0. This making sense? Okay. And so x equals, so if I just solve for this, I'm going to get the global optimum is going to be, if I just move x0 minus f prime of x divided by f double prime of x0, right? Does that make sense? Yes or no? Okay. Now compare this with my gradient descent rule. And what is my optimum step size? 1 over f double prime. If you just take a step size that's exactly equal to the inverse of the second derivative, it doesn't matter where you start from, you're going to get to the solution in one step, right? And so that's basically it. There is a one-step solution where if my step size is exactly equal to what on earth is happening? Okay, if my step size is exactly equal to the inverse of the second derivative, which is simply going to be my constant a, right? I'm going to get to my solution in one step. Everybody with me so far? Okay, so if my so here's the gradient descent property. Okay, I have my bowl. This is my optimum. I start at some point, and I'm going to use the rule xk equals xk minus 1 minus of 1 over f double prime at xk minus 1 times f prime of xk minus 1, right? And so this gradient descent rule is always going to be getting me to my optimum in one step. And so this is my step size. Eta equals 1 over f double prime at xk. If I do so, I'm going to go from here to here in one step. If my eta is less than this term, what happens?
They need more than it doesn't quite yet reach them.
If eta is less than the optimum, what will happen?
You need more steps.
I will need more steps, right? So I'm going to go here and here and here, and I'm going to go down, right? If eta is greater than 1 over f double prime, what's going to happen?
It misses the optimum.
What will happen?
It might diverge.
Divergence, does it diverge?
Might.
Does it diverge? It's going to go here, right? It's going to overshoot. It's going to go here, but then it's the next time it's going to go here, and the next time it's going to go here. It's still going to get to the optimum, right? What must the step size be for me to never actually go down the bowl? Yeah, Chetan?
If you're equal to or greater than like the exact
Yes, and what would that step size be?
2 times
2 times. Lovely, right? If my step size is, if my eta is equals 2 over f double prime, I'm just going to go here. I'm going to keep bouncing back and forth. If eta is greater than 2f double prime, I'm just going to go up and walk out of the bowl. Make sense to everybody? And so that's the property we're going to find. That if your step size is more than twice the, if your step size is exactly the optimal step size, you're going to get there in one step. If it's less than the optimal step size, you're going to walk very slowly towards the solution. If it's greater than the optimal step size, right, again, until it approaches twice the optimal step size, the speed at which you approach the solution actually goes down, because now you're going to be bouncing back and forth as you go down slowly, right? And then when you cross twice the optimal step size, you actually begin to diverge. At twice the optimal step size, you're never actually going to ever go down, right? That makes sense to everybody? And so we have an optimal step size. Now, for a generic differentiable convex function, it's not going to be quadratic, it's going to be some other shape. But then I can always write a Taylor series approximation of that kind and truncate it after 2 terms. And for each of those, and then so basically this is the famous Newton's method. You're going to be taking a Taylor series, second order Taylor series approximation. And then at each point you can make a quadratic approximation and go to the optimum in a single step. But then you get to a new location and then you make a new quadratic approximation and go to the optimum in a single step and so on. But regardless, at each point, if your step size is more than twice the inverse of the second derivative, there is a high likelihood that you're going to bounce up instead of coming down. Make sense? Right. So now that was for a function of a single variable, okay? Things get more interesting when you look at functions of multiple variables. When I've got multiple variables, it still is a quadratic function is still going to be have quadratic terms, and it's going to look like so, which is now x is a vector, right? And so I'm going to say f of x equals half of x transpose ax plus b transpose x plus c. You'll observe that if x is a column vector, A is a matrix, this is going to end up being a quadratic function, right? Now, for convenience sake, this doesn't have to hold, but let's assume A is a diagonal matrix, right? If A is a diagonal matrix, then I can write this as if A is a diagonal matrix, A will have this form. Let's just assume 2 variables for now. It's going to be A11, 0, 0, A22, right? So this is going to be half of x1, x2, A11, 0, 0, A22, x1, x2, plus b1, b2 times x1, x2 plus c. This would be my quadratic, correct? Everybody with me? Right. So what can you write it in scalar form, Surya? What is this going to be?
B1 x1. Oh, A11 x1
A11 x1
plus A22. Oh,
what does this become? Matrix multiplication, you can't have forgotten.
A11 x1 square.
This is going to become half of A11 x1 squared plus A22 x2 squared, right? Plus b1 x1 plus b2 x2 plus c. Correct? This making sense? Even if it's A is a full matrix, if I rotate this space, it's going to come back to the same form, okay? And so now this actually ends up being the sum of a quadratic in x1 and a quadratic in, there's a half here, sorry, and a quadratic in x2 and a constant, right? If I'm minimizing this, I can minimize each of the quadratics independently because they're just the sums of 2 independent quadratics, right? What is the optimal step size for the first quadratic in x1? 1 over A11. And what's the optimal step size for the second one? 1 over A22, right? And this causes a problem. So let's see what happens over here. So I can write this, when A is diagonal, I can write this as a sum of quadratics in the individual variables, right? And if I plot the function, it's going to look like this. This is my equal value contour. If I plot it as a function, so at any given value of x2, if I change the value of x2, this, as far as x1 is concerned, this is just a constant, which changes, as I keep, this is just an additive term that changes as I change x2, right? The shape of the quadratic itself stays the same. So with respect to x1, I have a bowl whose height changes when I change x2, right? So also with respect to x2, I'm going to have a bowl whose height changes as I change x1. So the overall objective function, if I draw the equal value contours, it's going to look like this overall function. If I take slices at different values of x1, all the slices are going to be bowls at different heights, and the minima are all going to be at the same location, right? So also, if I take slices along the other direction, all of those slices are also going to be bowls with minima with the minima at the same location at different heights. Is that picture making sense? Right? Now here's the problem, right? This means that if I look at the function, the function as just a function overall, the multivariate function is a function of just the first variable. Regardless of the value of the second variable, it's going to be a bowl, and the minima are at the same location. Also, with respect to the second variable, it's always a bowl, and while the height of the minimum will change with x1, the location will not, right? So why does this do this, right? Now, when I'm using a gradient descent rule, I'm always taking a step against the gradient, right? So the gradient is in the direction of increase, so away from the center, and the step I'm going to be taking is towards the center. But we saw this in a couple of classes ago. The gradient is always 90 degrees to the equal value contour, right? So the gradient, see those ellipses? At any point, the gradient is at 90 degrees to that ellipse, okay? And now we know that the optimum step size for each variable is the inverse of the second derivative, which is the inverse of the curvature with respect to that variable, right? Now, what happens? Here's an example. This is a function of two variables. The curvatures for the two sides may not be the same, right? And so, again, when I'm using gradient descent, I'm using the same step size for every variable, right? I'm taking a step against the gradient. And so, if I have something of this kind, where I'm going to be separately drawing the function. It's a function of two variables. I'm going to be separately drawing it as a function of the first variable and a function of the second variable, because we know that we can treat those two bowls independently, right? And so let's say for against x1, the function looks like so, right? Against x2, the function looks like so. Which of these has the higher quadratic term? The one on the left has the higher quadratic term because it's steeper, right? So this is, let me call this A11. This is the curvature here. A12, A22, this is the curvature here, and clearly A11 is greater than A22 in my example, right? So now this guy is a large number, correct? What is the optimal step size for this one? 1 over A11, right? If I do this from here, I'm going to get here in one step. At the same time, I'm going to be here. Is that going to be optimal for this guy? What will happen? I'm going to be crawling to the answer, correct? So suppose I want it to be faster, and I don't want it to crawl to an answer for A22, right? So then I'm going to take, what is the optimal step size for the second variable? 1 over A22. So then 1 over A22 will get me to the answer here in one shot. What will happen on this side? That step size is going to be too large. It's going to bounce out, right? And so here's what you're going to happen. Here's a little example. I have the optimal step sizes of 1 and 0.33 along the two directions. If the optimal step size is 1, it means the curvature is 1, right? So that's speaking of the vertical direction. optimal step size is 0.33, means the curvature is 3, right? That's the horizontal direction where the ellipses are narrow, right? And so here, where's my tripod? Yeah, tripod. This is, if I set my step size to be equal to 2.1, say 0.7, right? If I step my optimal my step size to be 0.7, then over here, for this guy, it's pretty good at 0.7, right? So it's going to sort of monotonically come to the solution along the vertical axis. It's too large along the horizontal axis. The solution is going to diverge. Make sense? Right? Over here, I have chosen my optimal step size to be exactly equal to 0.66. What happens if I've chosen my step size to be 0.66? What happens? What will happen? For the, yeah.
So it's less than the optimum for first one, so it will directly converge there, but
It's not going to diverge, it's exactly twice. It's going to keep bouncing around, right? And so you're going to see the behavior in the second one, right? Now, if I have a step size equal to 1.5 times 0.33, now both of them will converge, but it's going to be very slow for the first guy because, 1 times 0.33 is significantly lower than 1, right? And in the second case, it's going to converge, it's going to bounce around before it comes to a solution, right? Because it's greater than the optimal step size, it's just not greater than twice the optimal step size. And so here, I have the optimal step size. The step size is exactly 0.66. So in this direction, it gets there in one step, but in the vertical direction, it takes its time. And if both of them, and if it's lesser than, even 0.33, right? Then along both directions, it's going to come slowly to the optimum, right? So what does this tell me about the function and about optimization? Under what conditions, I don't generally know the function, right? But what is the condition I want for the function to be, for me to be able to optimize the function really quickly? What is the condition I would need? Do I want the two optimal step sizes to be very different? Yeah? Do I want the curvatures along the two directions to be very different? Because what happens then? One may converge and one may diverge, right? I ideally want the optimal step sizes to be the same for both directions. So what is a good function here? A good function that says one that has the same curvature along every direction, right? So the way you can actually quantify it is in terms of the, you want eta to be less than the step size for it to work should be less than twice the smallest optimal step size, right? But if there's a big gap between the optimal step sizes for the different directions, this means it's going to converge very, very slowly and never really get to an optimum. And so, this makes learning very slowly, right? Learning very slow. And so, and that was for quadratic functions. If I have a generic multivariate convex function, I can again take a Taylor series approximation, write it as a quadratic term, and in the case of the quadratic approximation, the curvature is going to be given by the Hessian, and the eigenvalues of the Hessians are going to give you the curvature along the different directions, right? And ideally, in the most ideal case, you want the curvature in every direction to be the same. In other words, you want the Hessian to have same identical eigenvalues along each direction. And as you increase the condition number of the Hessian matrix, which is the ratio of the largest to the smallest eigenvalues, the function becomes more and more wonky, flat in one direction and steep in the other, which makes it impossible to optimize. And so you generally want the largest and the smallest optimal step sizes to be as close as possible, right? But that's not always going to be the case. A good function is one where the largest and smallest optimal step sizes are close. A bad function is where there's a big range, and the goodness of a function can be sort of quantified in the ratio of the largest curvature and the smallest curvature. The larger this ratio is, the worse the function is for us to optimize. Everybody with me so far? Right. So this is great, right? You want the optimal step size to be less than twice the optimal step size for it to converge. Ideally, it must be close to the optimal step size, right? And if it's more than twice the optimal step size, it's going to diverge. But is this so? So this is lesson number 4 for the day, right? But is this always a bad thing? We've been speaking of convex objective functions. Your typical loss function is going to look like this. When you start off at some initial point, if you make sure that your curvature is, your step size matches the curvatures of wherever you currently are, you might find yourself in a small bowl and just going to a crappy local minimum, right? So initially, you want your step sizes to be large enough that you actually escape any local minima that you have. And global minima tend to have this property. Good global minima will be big, deep minima. And narrow minima and shallow stuff are typically going to be local minima, which are not very nice things. And so in the beginning, you don't really want your step size to be so small as to guarantee that you go directly to the bottom. In the beginning, you want it to be large enough that you escape. But then over time, you want to, you don't want to keep bouncing around all the time, right? Over time, you want to evolve your step size, your learning rate, so that you begin to converge. And so if you take a large steps in the beginning and then keep decreasing your step sizes, eventually you're going to find yourself in a bowl which is big enough that your step size is too small for you to jump out. And then you'll go to the minimum. And such bowls, like the two big bowls that you have, these are good local minima to get to. They might even be optimal global minimum. And so our requirement is that we want to start with a large learning rate, greater than 2 if I'm Hessian normalizing, otherwise 2 times the inverse of the smallest eigenvalue of the Hessian, and then gradually reduce it with iterations. Now if you're doing your homework, this is basically what you're doing. Your learning rate is decreasing with iterations because it actually allows you to step out of local minima and get to a global or something which is a better minimum, right? So, and there are many plans for how you can keep decreasing your step sizes. There's linear decay where you linearly decay the step size in inverse proportion to the iteration number. You have quadratic decay where you reduce the step size in proportion to 1 over the square of the iteration number. You have exponential decay and many others. We'll take another look at this in a couple of classes, in the next class, right? So at each iteration, you're going to be shrinking your step size, but initially it's going to be, the learning rate is going to be large. Questions? Questions? Okay, why are we having this problem? Why do I have this crazy problem that I showed you in this figure? Anyone? Yes?
Because the learning rates for the different variables are different because the curvature of those functions are different.
We are forcing the same learning rate for every variable, right? If you're using classical gradient descent, you're forcing eta to be the same for every variable. And that's why we have this problem, right? So what would be a more reasonable thing for us to do? Have the learning rate be different for different variables. But then how do we know what the learning rate is? So there are a couple of different solutions that come up. So his story so far, gradient descent can miss obvious answers. It's a good thing. Convergence issues occur because the loss surface has many saddle points. And gradient descent can stagnate on saddle points. Vanilla gradient descent may converge or converge too slowly because the optimal learning rate for one component may be too high or too low for the other components, right? And so there's a point. Okay. Does anybody want to tell me that first statement is true? Yes or no? Yes. Second one? And the third? Okay. Right, only the first one is true. Beautiful. Okay. So many of the divergence causing learning rates may not be a bad thing for ugly loss functions. Decaying the learning rate provides a good compromise between escaping local minima and convergence. But many of the convergence issues arise because we force the same learning rate on all parameters, right? So what is the solution? Let's take a step back. The problem of requiring a fixed step size across all dimensions is something we would like to avoid. But if you're not doing this, you no longer are performing gradient descent. Remember this, gradient is walking against the gradient, which means the gradient is a vector of partial derivatives. You must be going against it, which means you are taking the same step size learning rate for all components, right? We're going to stop doing gradient descent. I will still call it gradient descent, but really it's not gradient descent anymore, okay? And so there have been various great derivative inspired algorithms that use derivative information for trends but don't follow them very religiously. So RPROP, called resilient prop, and quick prop. Quick prop was very popular, and these are still two of the best optimization algorithms around. Don't need a lot of thinking. Quick prop was invented by our own Scott Fahlman, and these were huge till Adam and such those other algorithms came along. So I'm going to take a look at RProp. It's a very simple algorithm that you're going to follow independently for every variable. And what you will do is this. You're going to take a step. At each point you can check the derivative, right? And you're going to take and say the derivative tells me I must go forward because the derivative of the loss is negative. So now I take a step forward. If I take a step forward and the loss is still decreasing, if the derivative is still decreasing, still negative, have I gone in a good direction? Yes or no? I'm going downhill, right? I want to go up downhill. I take a step and I find that I'm going downhill. Is that a good direction? Yes. Should I increase my step size or decrease it? I'm going in the correct direction, so I'm going to get more confident, right? I'm going to take a slightly bigger step. I'm still going down. I'm going to take an even bigger step, right? But then at some point I will overshoot. Then what do? I can go back and repeat the process, but now I'll reduce my step size and repeat the same process. It's a very simple algorithm, right? Am I ever taking the value of the derivative into consideration? I'm just looking at the direction. I'm not looking at how much the derivative is. You're ignoring the magnitude of the derivative. You're only using the sign. So you start off with some initial value, compute the derivative, and can take a step according to the derivative. Forward if the derivative is negative, backward if the derivative is positive, right? And then you move to the newest location, and then check your derivative. Right? The yellow arrow shows you the sign of the direction of the derivative. If you're moving in the correct direction, then you're going to increase your step size. So your initial step size is some delta W0, right? Delta W. Then you're going to increase your step size by some factor alpha, which is greater than 1. And then you check the derivative sign again. If the derivative sign hasn't changed, you increase the step size again by a factor alpha, which is greater than 1, right? And you keep doing this, and then at some point, you're going to overshoot the minimum. Then you say, oops, I've gone too far. So then you go back. And now decrease the step size by some factor beta. And now use this new step size and repeat the same process. That makes sense? Right? Very simple, right? And you'd be doing this independently for every variable. So this is resilient prop. And so yeah, after shrinking the step size, you take the smaller step size forward. So here, this is a very simplified pseudocode for RProp. You're going to be initializing your step sizes. And at each point, you're going to just compute the derivative. And then all you do is to check if the previous value of the derivative and the current value of the derivative is the same. If they are the same, you're going to increase your step size. Otherwise, you're going to go back and decrease your step size. You never actually look at the value of the step size itself, and then to make sure that things don't go completely bonkers, you put a ceiling on how large your step can be, right? And also, if you're always shrinking your step size, at some point you're going to make it too small, so you also put a floor on how small the step size can be, and that's it. Okay, I'm speaking of the step, not the step size, but yeah. And so we will need backprop. We will need backprop to compute the derivative because we want the sign of the derivative. You'll do all that work, but then you'll throw away the value of the derivative itself. You're only going to use the sign. Right? Questions, anybody? I won't go through the code. The intuition is simple enough that you can code it trivially, right? So rprop is a very simple first order algorithm that's frequently much more efficient than gradient descent and can be competitive against the more advanced methods that we use today. It only makes minimal assumptions about the loss function. It doesn't assume convexity, nothing, right? And works quite well. So here's the third poll. Three seconds, guys. Okay. So, Juho, do you want to answer this question? First one, Colton. The derivative of the loss with respect to W, computed using the current estimate, is positive. After taking a step, the sign of the derivative becomes negative. So what would you want to?
We want to take a step in the like. I think you go in the same direction.
The sign of the derivative has changed. What would you do?
Then you flip.
So that means you overshot. So then you go back to the original location, right? And then take a smaller step. Isn't that what we said? Okay. Questions? So this was one way of dealing with things, right? Trying to make the steps on the individual directions independent of one another. There's a second technique called quick prop, which looks like a lot like Newton's updates, and this actually uses estimates for second derivatives, and when it works really nicely. One of the fastest training algorithms for many machine learning problems. I'm not going to go over the slides. It's the algorithm, but it's on the slides. So we have that gradient descent can miss obvious answers, which may be a good thing. Vanilla gradient descent may be too slow or unstable due to the differences between dimensions. I haven't mentioned it, but second order techniques will try to rescale the variable so that the curvature in each direction is more or less the same. And then you eliminated this problem of different curvatures along different directions, right? And then adaptive or decaying learning rates we saw can help us escape poor local minima and converge. And methods that decouple the dimensions can improve convergence. You guys with me? Okay. So let's take a closer look. With dimension independent learning rates, right, or the solution will converge smoothly in some directions and oscillate in other directions, right? But in the process of doing so, if you just track the solutions, it's telling us a story, is it not? If I find that I'm going back and forth along x2, then what is it telling me? It's telling me that my step size for x2 is too large. If I'm just going smoothly forward along x1, it's telling me my step size is okay. Maybe I can even increase it, right? Just by looking at how my solution is behaving, I can improve the behavior of my optimization. So this gives rise to momentum methods. There are a couple of different momentum methods. We want to keep track of oscillations. We want to emphasize steps in directions that converge smoothly, and you want to sort of reduce them in directions which oscillate. And the way we do it is by actually tracking the gradient. So if I've got the gradient, right, the gradient has a partial derivative along each component. If the partial derivative, now this is just like R prop, right? If the partial derivative is in the same direction in some, has the same sign in some direction, then I can keep the partial derivative. If the partial derivative begins to flip back and forth, flip its sign, then I want to shrink the value of this derivative in that direction, right? Can I couple this and write this as a single formula? Can we R prop was only looking at the sign of the derivative. Can we do R prop while we also consider the magnitude of the derivative? The way we will do it is to use a running average of the derivative in each direction. You want to maintain a running average of all the past steps. If I'm maintaining a running average, then if I'm sort of taking steady steps in some direction, then the running average is going to keep giving me a positive value in that direction. Whereas if I'm doing this, going back and forth, then the running average is going to slowly cancel, the positives are going to cancel out the negatives, and my steps are going to get smaller and smaller in that direction. Make sense? Right? So if I'm oscillating, the running average is going to keep get smaller and smaller and smaller and smaller till it becomes almost, something where I'm not bouncing back and forth. Whereas if I'm going steadily forward, the running average is going to keep pointing forward to me. That's the momentum technique. So the momentum technique does something very simple. You take the current estimate, so at each step, at each update, you remember what the previous step you took was, and then you know the gradient at the current step, and to the gradient you add some scaled version of the previous step. This is basically a running average, right? So I've got some step. The equation for running averages is fairly straightforward. We all know this. If I have the step that I'm taking, not the step size, not the learning rate, but the step. If my delta W, if my step is Sk is going to be some alpha time Sk plus 1 plus correction, right? This is all plus the new value that you've got. You're always sort of taking the previous value, scaling it down, and adding the new contribution. And in our case, we know that the correction is always the negative of the gradient, right? And so our step size is simply, our step is going to be beta times the previous step minus plus the negative of the gradient, right? A scale negative of the gradient. And this correction term, this step size, this step is what we are going to be adding to our current estimate. Again, equations don't tell the story. It's kind of convenient to look at the pictures, and pictures are very nice. So let's see how this works. I have, so the intuition over here is that if you're doing something of this kind, then the directions where you're moving back and forth, the steps are going to get smaller. In the directions where you're moving smoothly, the steps are going to get larger. And so here is a picture. I have a pseudocode, I'll skip it. But let's say this is the last step that you took, right? Then at the current location, you will check the gradient, and you take a step against the gradient. That's the blue arrow, right? But to that step, you're going to add a scaled version of the previous step that you took. And that is going to be your new estimate. That makes sense to everybody? So at the current location, you know what the last step you took was. So then you're going to find out which way the gradient tells you to move, but you're not just moving there. To that, you're adding a scaled version of the previous step to get you the net update. Everyone with me? Right? Code won't make so much sense as much as pictures. And here something cool falls out. There's actually once you see this in pictures, you realize you can change the order, which is this. Instead of taking a step against the gradient and then adding in the previous, a scaled version of the previous step, I can change the order, and that's going to give you a completely different solution. So this is what we did. First, we computed the gradient and took a step against it. That was 1. And then you added beta times the previous step, shown by the red line, to get the new one, right? Instead, what I will do is I'll first take a step, beta times the previous step, and then compute the gradient and go against the gradient. It's still the same two operations, but in reversed order, right? And that's going to be my new step. And this is called Nesterov's accelerated gradient. And there's a little bit of nice math to prove that this is always going to be much better than doing it the other way around. And it's apparently the optimal thing to be doing. So here, look at what we are doing. So from the current location, we are taking a step, which is beta times the previous step size, then computing the gradient over there, right? And then the actual correction is going to be, again, the step plus the gradient, right? That's what you're adding to the update. Now, formulae, I don't know about you, but when I look at the formulae, my eyes glaze over, and it doesn't, I don't quite get a feel for it always, but when I look at the picture, it just tells me exactly what I'm doing. Yeah.
Why is this more optimal?
You'll have to see Nesterov's paper for it. But we'll have some more pictures in the next class, and you'll see that actually you can see how this works. Actually, this was from Hinton's method. This was from Hinton. Okay. So here is the comparison of the two. If I'm doing momentum, if I've taken this previous step and come here, then I take the gradient and go here, and then add a scaled version of the previous step, that's going to take me here. Right? Whereas if I'm just taking the scaled version of the previous step and then taking the gradient, that's getting me here. And in the case of the convex function, you can see that the second one actually gets me to the much closer to the optimum, right? So for convex function, the second approach actually is much better. So anyway, we are at the end of today's class on time. I have pseudocode for Nesterov's method. These are momentum and trend-based methods. We're going to get back to this again very soon. There's a final poll for those who want to take it, and then we're done. Okay, since this was just a yes/no poll, we'll give you less time. What's the answer, guys? False. Can Tirth, what's the answer? False. Does everybody agree it's false? Okay. Momentum only changes the step size, right? On a flat surface if you've got a constant slope, then the running average is going to be pretty much the same as the gradient itself. So nothing will change. Okay, thank you. I'll see you in the next class. The stories of our slide.